The two basic circuit elements with differential equation models are the capacitor and the inductor. An inductor is formed when a wire is coiled around a core, as shown. When current flows through a wire, it creates a magnetic field around the wire, as shown in the middle graphic. The orientation of the magnetic field is determined by the right-hand rule. That is, if you grab the wire with your right hand with your thumb pointing in the direction of the current, your fingers will be pointing in the direction of the magnetic field. When wire is wrapped around a coil of N turns, the strength of the magnetic field is multiplied by a factor of N. The core of the inductor can be air, iron, or other material. The magnetic properties of the core affect the strength of the magnetic field generated by the inductor. Looking at the third diagram, if the coil is wrapped clockwise, starting from the right and going right to left, and the current is flowing in the coil from right to left, the direction of the magnetic field in and around the inductor is as shown. If the direction of the current is reversed, the direction of the magnetic field is reversed, as shown in the bottom diagram. The magnetic field stores energy proportional to the square of the current through the inductor, and energy is required to create it. The expenditure of energy creates a voltage drop across the inductor, and hence an applied voltage is required to increase current in the inductor and the strength of the magnetic field. The inductor model is given by the differential equation. The rate of change of current in the inductor equals the voltage applied to the inductor divided by the inductance of the inductor measured in henries, after the American scientist Joseph Henry, who discovered inductance at about the same time and independently of Michael Faraday in England in the 19th century. Looking at the top diagram and with the terminals labeled as shown, a positive voltage increases the current and the magnetic field becomes stronger. A negative applied voltage causes the magnetic field to collapse. When the magnetic field is collapsing, it supplies energy to push the current in the same direction it is flowing and against the negative voltage. In the bottom diagram, negative current is flowing in the inductor, which is increased by a negative applied voltage and decreased by a positive applied voltage. If it's difficult for you to picture, and it was for me, a collapsing magnetic field pushing current through a wire, I have an alternative visualization. Picture the inductor as a turbine with the energy stored in the spinning rotor of the turbine. An applied positive voltage increases the positive flow through the turbine and hence the speed of the rotor blades. Energy is being supplied to the inductor and stored in the spinning rotor. When there is no applied voltage, the blades continue to spin and the current flows against no resistance. When there is a negative applied voltage, the blades continue spinning, pushing the current against the negative voltage and losing energy and slowing down in the process. When there is no current, the rotor is stopped. If the negative voltage continues, the blades will start spinning in the opposite direction. Let's look at some simple circuits containing inductors. The simplest is with a wire and an inductor. We can initialize the current with an initial current of 2 amps. What happens then? Since 2 amps is flowing at time t equals 0, the rotor blades are spinning, and since there is no opposing voltage, they will continue to spin, and the 2 amp current will continue indefinitely. We'll write a program for simulating the circuits in this video, and with the battery voltage set to 0 and the resistance set to 0, and the initial inductor current set to 2, this graph shows the result. The graph is a constant value 2, which can't be seen in the slide because it coincides with the top edge of the graph. There is a MATLAB command for manipulating graph axis limits, but we won't bother with it here. What happens when we add a resistor? Now the inductor sees a negative voltage created by the voltage drop across the resistor, and this negative voltage causes the magnetic field in the inductor to slowly collapse. The graph shows the result. With the initial current set to 2 amps, and with the current graphed in blue, we see from the graph that it slowly decreases to 0. The resistor voltage is graphed in red. The resistor value is 5 ohms and the initial current is 2 amps. So the resistor voltage at t equals 0 equals 5 times 2 or 10 volts. It decreases to 0 along with the current. From Kirchhoff's law, the sum of the resistor voltage and the inductor voltage, graphed in green, is 0. So the inductor sees an applied voltage at t equals 0 of minus 10 volts, and that increases towards 0 as the current decreases. We will do the computations for this circuit. The model will have one state variable, the inductor current, and the inductor model provides a differential equation for it, namely, the rate of change of the inductor current equals the inductor voltage divided by the inductor inductance L. We need to write the inductor voltage as a function of the state variable, and since the inductor voltage and resistor voltage sum to 0, the inductor voltage is the negative of the resistor voltage. And from the resistor model, i.e. Ohm's law, the resistor voltage is the current times R. So the inductor voltage equals the negative of the resistor voltage and hence equals the negative of the current times R. Thus, the rate of change for the inductor current is the rate of change of inductor current equals the negative of the resistor voltage divided by L, which equals the negative of the current times R divided by L. So we can write our computational equation. The current at time ti plus 1 equals the current at time ti plus the derivative of the current at time ti times dt. And using the differential equation to substitute for the derivative of the current at time ti, we have current of time ti plus the negative of the current at time ti times r divided by L times dt. With R equals 5 ohms, L equals 1 Henry, an initial current of 2 amps, and dt equals 0.02 seconds, we can do a few calculations by hand. I at 0.02 seconds equals I at 0 minus I at 0 times R divided by L times 0.02, and substituting the numbers we get 1.8 amps. I at 400ths of a second equals I at 200ths of a second minus I at 200ths of a second times R divided by L times 0.02. Substituting the numbers, we get 1.62 amps. Next circuit. This circuit contains an inductor and a battery and no resistors. Can you predict what will happen when the switch is closed? Here it is. Since the battery voltage is constant, there's a constant applied voltage applied to the inductor, so the inductor current increases linearly. Since there is no resistor in the circuit, no voltage develops to resist the increase in current, and it increases indefinitely until the battery fails. Finally, a circuit with a battery, a resistor, and an inductor. At time t equals 0, we close the switch. What happens? With no inductor in the circuit, the current would immediately start flowing. However, there is an inductor in the circuit, and it limits the rate of increase in current in the inductor to I prime of 0 equals BL of 0 divided by L. That is, the current in the inductor at time t equals 0 is 0, and it ramps up. There can be no instantaneous current in an inductor. By analogy, the turbine rotor has to be spun up. It can't acquire an instantaneous spin rate. Kirchhoff's voltage law states that the sum of the voltages in the loop equals 0. So with the polarities assigned to the resistor and inductor in the diagram, we have the battery voltage minus the resistor voltage minus the inductor voltage equals 0, so that the inductor voltage equals the battery voltage minus the resistor voltage. So the model for the circuit is the rate of change of inductor current, that is the current in the circuit, equals the inductor voltage divided by L, which equals the battery voltage minus the resistor voltage divided by L, which equals the battery voltage minus I times the resistance divided by L. What happens when the switch closes? The inductor current is graphed in blue, and it starts at 0 and ramps up to 2 amps. The inductor voltage is graphed in green, and at t equals 0, the inductor sees the full battery voltage of 10 volts, and that decreases as increasing current creates a voltage drop in the resistor. The resistor voltage is graphed in red. Since current is 0 at time t equals 0, the resistor voltage is 0 at time t equals 0, and it ramps up with increasing current. The final value of the resistor voltage is 10 volts. The final value of the inductor voltage is 0 volts, and the final current value is 2 amps. The assignment is to simulate all the circuits in the video, and one program will do it, and also to generate the graphs that you see in video.